Hi friends, welcome back to Edupedia World. In our previous lecture, we finished the topic force. Today we will begin the topic work, energy and power. This is a broad topic, but today's lecture we will focus on work. We will see the definition of work and the mathematical formulation. We will discuss special cases. We will see the units of work, and then we will see a simple example demonstrating how to do the numericals of work. Let us start with our lecture today. Work in the traditional sense means carrying out some activity, but that is not how we define work in physics. In physics, work is said to be done when a force moves a body. So an applied force produces a displacement. So force produces displacement. Only when a force produces a displacement, then we say that a work has been done. That is how work is defined in physics. Now, an example would be you have a box lying on a floor, you push it, you apply a force on it, and the box moves. Then you say that the force has produced a displacement, hence the work has been done. Now let us take another example where we push on the wall. A wall, how much soever effort you apply on the wall is not going to move from its place. It is going to stay there. As a result, there is no displacement of the wall. Therefore, even though we are applying a force, since there is no displacement, we say that no work is done. Therefore, an example of force producing displacement, hence producing work, is moving a box by applying force. In this, work is done. Second example, applying force on a wall, no work done. So it is clear that there is a need for a displacement by the force for work to be done. This is the qualitative treatment. Now, what is the quantitative treatment of work? What is the formula for work? Work mathematically is defined as the product of force applied and displacement in direction of the applied force. In direction of the applied force. So mathematically, work is force applied into displacement in the direction of applied force. What do we mean by in the direction of applied force? Let us take an example to illustrate the point. Here is a box lying on the floor. You apply a force F parallel to the floor F, and this makes the box move a distance of d. Then since the displacement, that is d, is in the direction of the applied force, that is this parallel to the floor, then we can say that the work done is equal to force times displacement. But in a different case, suppose you have the same box which is lying on the same floor. This is the box lying on the same floor, but now the force applied is not parallel to the floor. Now the force applied is something like this. It is like this, which means this is the force, and this force is making an angle theta with the floor. And now the box has moved the same distance. Let's say that the box has come over here, so the displacement movement of the box is the same, that is, it moves a distance of d. We have the same force applied F, we have the same displacement d, but in the second case the force is applied at an angle theta. So what do we have to do? We have to find the force along the direction of the displacement, or the displacement along the direction of the force. Let us do it by the first way. Let us find the force along the direction of the displacement. So the force is something like this. This is F. This is the component of force in the direction of the displacement. So if this is F and if this is theta, then this is F cos theta. We see that the force applied in the direction of the displacement is F cos theta, and the displacement along that force is d. Therefore, the work in this case is F cos theta into d, that is Ft cos theta. So an additional factor of cos theta comes into picture in this example. Let us try to get the relation using the component of the distance or the component of the displacement in direction of the force, rather than taking the component of the force in the direction of the displacement. So we will take the force in this direction. We'll have the force in the existing direction, and basically what we need to do is we need to find the component of the d in this direction. So since this angle is theta, when we extend the force, then this angle turns out to be theta 2. Okay, and since this angle is theta, this is d, then the length, the component of d along the force, it would be d, this is theta, so cos theta. Therefore from this also we come to the conclusion that work done is equal to, now we will take this force F and we will take this displacement d cos theta. So ultimately both the methods to find work gives us the same result, that is F d cos theta. Now this FD cos theta is expressed as what is known as a dot product. We express this as, let me write over here, this is expressed as F dot D. This is called dot product. Dot product. What does dot product mean? Dot product is a mathematical representation whose equivalent is F D cos theta. So if we write a dot product A dot B, that inherently means A into B into cos theta, where theta is the angle between those two forces, those two vectors. Here the vectors are force and displacement. So theta is the angle between the two vectors. Therefore, using the concept of dot product, we can find out how much work is done in any case. If we know the angle between the force and the displacement, we can directly use this relation, force into displacement, into the angle between them, into the cos of angle between them. Next, let us see certain examples of work done in different scenarios of force and displacement. We will see two special cases. The first is when the angle between force and displacement is 0 degree, that is they both are in the same direction, and second is when they are at 90 degree, that is they are perpendicular to each other. So first is theta is equal to 0 degree. An example of this would be a ball falling from a height h to the surface of Earth. This height is h, the mass of the ball is m, and it falls from here and it lands over here. So what is happening here is that the force is the force of gravity, which is acting downward. And what is the magnitude of the force? It is mass into g. So mg is acting downward, and the displacement here is h. It is moving from here to here, so it is being displaced h in the downward direction. So both the force is acting downward and the displacement is in downward direction. Therefore, in this case, our work done is mg times h times cos 0. That gives us mgh. We see that if the angle between the force and the displacement is 0, then cos theta becomes 1, and we get work as force into displacement directly. In this case, that being mgh. And this mgh is actually defined as the work done by gravity. This is said to be work done by gravity. For the sake of completion of this discussion, work done by gravity, I will discuss another example in which we throw a ball upwards. Here what we are doing is from the floor or from the ground we are taking the ball and we are throwing it upwards, and it reaches a height of h, let's say. It goes from ground to h, but at any moment the force on the ball is always acting downward. So the force on the ball is always mg and it is acting downward. Therefore, what is happening in this case? In this case, our displacement is h upward, but the force is mg downward. As a result, what we can say is that the theta in this case is theta is equal to 180 degree. The force is downward, the displacement is upward, so the theta, the angle between them two, is 180 degree. As a result, the work done is mgh cos 180, and we know that cos 180 degree is -1. Therefore, work done is minus mgh. So in this case, when we throw the ball upward, negative work is being done by gravity because their direction of force and displacement are opposite. Now we have seen two special cases here actually. So I will mention this one as theta is equal to 180 degree. And the third case is when theta is 90 degree, or the force and the displacement are perpendicular to each other. One of the examples of this scenario is uniform circular motion, which we already discussed in our previous lecture. What happens in uniform circular motion? Let me draw it. Is that a particle moves in a circle, and as we discussed in uniform circular motion, at any point the velocity is tangential and the force acting is towards the center. As a result, at any given point, the displacement is perpendicular to the force at that point. Since force, this is the displacement, I'm writing it as s, or the velocity v, since displacement will be in the direction of the velocity, both will be in this direction, and this is the force, and these two are perpendicular to each other. The work done is equal to s into f into cos of 90. This turns out to be 0. That makes the whole thing 0. So in this case, when theta is 90 degree, no work will be done. Therefore, for the condition when net work done is 0 can be summed up as 0 work condition. First is there is no displacement. If there is no displacement, obviously there will be no work done. But even if there is a displacement, like in this case, if we were traveling a semicircle from here only till here, then we would have a displacement from here to here, that is something like this would have been the displacement. But since the force was perpendicular to the instantaneous displacement at each point, the work done would sum up to be zero. Therefore, the second condition is force and displacement are perpendicular to each other. These two are our conditions for zero work done, even when force is present. Obviously, if there is no force, there will be no work done. But these two are zero work conditions even in presence of force, even when force is present. So in special cases, we have seen the case when theta is 0 degrees, when theta is 180 degree, and now we saw when theta is 90 degree. Then we saw the two conditions for zero work done. We have a much clearer picture with these examples. Now let us see what are the units of work. The SI unit of work, SI unit is joule, J-O-U-L-E. It is represented as J. 1 joule is the amount of work done when a force of 1 Newton. 1 joule is amount of work done when a force of 1 Newton causes a displacement of 1 meter in the direction of force, So SI unit of work, joule, is the work done when a force of 1 Newton causes a displacement of 1 meter in direction of force. The CGS unit, on the other hand, is called erg, E-R-G, and 1 erg is work done when force of 1 dyne causes a displacement of 1 centimeter in direction of force. So what basically we see here is that since work is force into displacement, the units are derived from there. Force times displacement is the work. Now there are higher magnitude units, that would be 1 kilojoule is basically 10 to the power 3 joules. 1 megajoule is 10 to the power 5 joule, 10 to the power 6 joule. Let us now see the relation between the SI unit and the CGS unit. That is, how many ergs are 1 joule. 1 joule is 1 Newton into 1 meter. We know that 1 Newton is 10 to the power 5 dyne. This is from our previous lecture. And we know that 1 meter is 10 to the power 2 centimeter. Therefore, combining the two, we get that 1 joule is 10 to the power 7 dyne centimeter, and dyne centimeter is basically erg, so that turns out to be 10 to the power 7 erg. 10 to the power 7 times erg is 1 joule. Let us do a simple example to find out the work done by a force. The problem statement says that a force of 50 Newton is applied, and this displaces the body by 20 meters. The displacement is 20 meters. So force is equal to 50 Newton, displacement is equal to 20 meter, and it says that the force is applied at 30 degree to the direction of displacement. So if the displacement D is in this direction, the force F is at 30 degree. Therefore theta is equal to 30 degree. We can say that the component of force along the displacement is F cos theta, and therefore the work would be F cos theta into D. So as we have seen in the theory, work can be said to be F D cos theta, F times D times cos theta, where theta is the angle between force and the displacement. That gives us 50 into 20 into cos 30. Now cos 30 is root 3 by 2. So if you simplify it, you will get root 3 by 2, that is 500 root 3 joules. Why joules? Because our force is in Newton, which is the SI unit, and our displacement D is in meter, which is again the SI unit. So we have to express work in SI unit. Therefore our work turns out to be 500 times root 3 joule. This is a very preliminary example of work done. We will discuss several examples after we finish power in our next lecture. So that is our topic of discussion in next lecture, power and energy. And once we are done with that, we will see numericals, which will have components of work, components of energy done, energy required, and power too. Till our next lecture, have a great day. Goodbye.